I'm based out of the economics department. This paper is joint work with Nang Wang, who's based out of the Graduate School of Business, and Jinchan Yan, who is from the Shanghai University of Finance and Economics. So a quick motivation for our work, managing COVID-19 risk for not only our health, but also for our wealth requires a stochastic epidemic model. Large-scale computational models have played a leading role in managing the public health crisis thus far. But and for a variety of reasons, these models are actually not so easy for non-epidemiologists to use. And so from our views, to simultaneously manage the health and economic crisis that COVID-19 has now become, we think it's also useful to work with more parsimonious epidemic models that highlight really COVID-19 risk, and that's also tractable enough to be used by non-epidemiologists. So the risks that we have in mind are well documented in the epidemiology literature, which really emanates from stochastic transmission rates. So this stochasticity can come from superspreader events, whether climactic conditions, pathogen mutations, or just simply unpredictable social behaviors. So we'll start with the classic deterministic epidemic model that's probably familiar to everybody in this audience, captured in equation 1. IT is the fraction of the population that's infected, beta is the transmission rate, and gamma is the exit rate from the infected state. We make sort of the usual assumptions of homogeneous mixing in the population, no births or deaths, and the population is normalized to 1, and everyone can potentially be infected. We're going to just work with 2 compartments. People can either be infected or susceptible. So we know this deviates from kind of richer SIR or SEIR models that are more widely used. So there's a few reasons why we're going to focus on this sort of SIS model. I think the first and most important reason is tractability. You'll see that the tractability affords us to really transparently highlight the risk of COVID-19. The other is also, there's no consensus at this point that getting COVID-19 confers any long-lasting immunity. And for many of our economic calculations of the damage of COVID-19 to our wealth, we're really interested in making longer-term forecasts. So we'll go from a deterministic model to a stochastic model by simply replacing beta, the transmission rate, with a stochastic rate, beta tilde. Over some small increment of time delta, we can think about the amount of transmission as being driven by 2 pieces, a deterministic piece or predictable piece, which is the beta delta, and also a random piece, which is captured by the random variable epsilon. So what we think of is that over every day, there can just be random draws of this variable. Okay, and you can think about these random variables as being drawn not only through time, but also across different countries or locations within a country. We're going to work with continued time formulation, where we're going to basically take delta to a very small infinitesimal limit and essentially work with what are called diffusion processes. In particular, we're going to have a very simple diffusion process for the transmission that's captured by the sigma dz term. Z is the standard Brownian motion. So sigma is really this new parameter that we want to highlight that captures COVID-19 risk. If you substitute this beta tilde dt term for the usual beta dt term in the deterministic epidemic model, you'll come to equation 2, which is essentially our 3-parameter nonlinear epidemic process. So the only kind of difference from the deterministic setting is really this last term highlighted in blue involving the parameter sigma, which is the COVID-19 risk. This process is stationary in the long run, but it's useful to highlight that at the very early stages, when everyone basically is not infected yet, you can just see that if you drop the 1 minus IT term, that essentially infections follow something like a geometric Brownian motion. That is, in the beginning, it's not really the reproduction number per se that's driving infections. It's really basically draws of this random variable ZT, captured by this term here, sigma ZT. So an area that basically gets a lot of bad shocks, we're just going to end up having a lot of infections. And some other areas may get very good shocks and end up not having any infections. That is, randomness plays a huge role in the transition dynamics associated with COVID-19. The usefulness of this nonlinear process is that we can calculate analytically the conditional density function. That's going to basically characterize and allow us to look at infections in the population, the fraction of infections in the population at any given point in time, and to basically give an entire distribution of possible outcomes for COVID-19. So why is this parsimonious model useful? Because ultimately we also have to deal with an economic crisis, right? i.e. COVID-19 is a risk to our wealth. And what we want to do is we want to link essentially epidemic data or epidemic structural parameters to an economic framework that allows us to simultaneously assess the damage that COVID-19 is doing to our wealth. And the way we'll do this is we'll introduce infections, the transmission rates, and also the volatility of COVID-19, and allow it to affect potentially the earnings of the companies that we invested. So for instance, think about Delta Airlines, think about the retail companies. All of these industries have been adversely affected now that COVID-19 has arrived. And so COVID-19 can affect, for instance, earnings growth. You typically think that as the infections go up, the earnings growth of companies could go down. It can also affect the volatility of earnings of these companies. And another channel is that COVID-19 now has basically created a new source of aggregate or macroeconomic risk. That is, when stochastic transmission rates get adverse realizations, i.e. there's high stochastic transmission, the risk in the economy also goes up. If we can tie then all of this epidemic data to earnings data for companies and basically come to a pricing equation that essentially captures our wealth. So that's given by equation 4. So when we think about the valuation of our wealth, it's really about discounting all of the profits that the companies, of the industries that run the economy, and discounting them back at some discount rate captured by this MS term. So YS is the earnings generated by different companies in the economy. So a very simple way to introduce epidemic processes into economics or into valuations is through 2 equations, equations 5 and 6. Equation 5 basically says that when there's stochastic transmission shocks captured by the DZ term, that's going to influence basically the risk in the economy. So we think that higher transmission rates mean basically more risk for the economy. And second is through basically the earnings or the cash flows of the companies themselves. Right? The level of infections will of course adversely affect the growth of earnings and also the volatility of earnings. And of course, the stochastic transmission rates could also directly impact earnings of companies themselves. The other terms highlighted in black just capture normal goings on, in other words, standard other macroeconomic factors that we typically think would apply, but now basically get drowned out or dominated by epidemic risk. The tractability of the epidemic model then allows us to calculate in one uniform setup also the valuations of companies. Right? In other words, when we think about the impact of COVID-19 on the airlines, which have been largely decimated in terms of their value, we want to basically link this to epidemic data. So we can calculate the asset value as a PT that's going to depend on the earnings in the economy and also on infections in the economy. Okay, and in particular, we'll highlight that really the price ratios, that is the valuations that we give to our companies, is going to really directly depend on infections. And this price is going to be determined by another equation, which is equation 7, that essentially is a simple ordinary differential equation, and one can solve it and basically back out the impact of infections on valuations of companies. The one thing we'll highlight immediately is that when thinking about epidemic risk or the risk to health, the reproduction number has played a huge role. But when you think about the economic crisis, right, not only is it about the reproduction number, but it's really about the risk. That plays an equally important role. And this is captured by equation 8 that basically says that for any given transmission rate beta in the economy, right, you have to basically also account for the fact that higher risk essentially transforms into a higher reproduction number. And that of course means more adverse effects for companies and their earnings. So we take data from the Johns Hopkins data repository that's got confirmed new cases, deaths, and recoveries each day starting on January 22nd. We calculate our variable, IT, as the number of net outstanding cases on a given day divided by the population. We're going to focus on 16 high-risk countries in the period of January to February. This is basically China and the regions with significant air travel connected to China. Here's what the data looks like. I plot, obviously, we're not going to plot all the countries, but I'm going to plot kind of 4 of the countries that have been widely talked about: China, Singapore, Italy, and the US. The gray areas are the 95% confidence intervals, and the dots are basically daily dots, capturing daily changes in the log of the fraction infected. One thing to note is there's just a huge amount of stochasticity on a daily basis in terms of these infections, right? That's sort of basically the premise. And we think that, obviously this is understood in the epidemiology literature, but from the point of view of modeling the economic damage, this really needs to be highlighted and brought out. You can see that, for instance, if you look at Singapore, right, they were able to bring down some of their stochasticity, they were able to bring down their infection numbers, but then basically it pops back up again in their so-called second wave. So let's talk about how we calibrate and estimate the model. There are three parameters. The parameter gamma, which captures the exit rate, we think that individuals are infectious for a period of about 5 to 14 days. Typically in large-scale epidemial models, gamma is modeled as a distribution. It's not something that's sort of estimated per se, given sort of the fact that there's a lot of variance across individuals in terms of how long they're infectious. For our purposes, we're going to set it to the higher limit, which is 14 days. We've also experimented with other specifications, such as, for instance, 10 days of infectiousness. Then we can estimate beta and sigma squared in a pretty straightforward manner without needing any type of simulations per se. So this is what we do. And for every country, we can simply look at the new cases and estimate, of course, beta and sigma squared. And here, what I'm reporting in this table is really the distribution across the 16 countries. Okay, and I'm going to just only look at January and February, just because we think this is capturing the early dynamics of COVID-19 before a lot of interventions by governments and changes in individual behavior come in. The thing to note is that what we're gonna basically simply have one model for all 16 countries, and the estimates we'll use is simply going to be the mean, okay, of beta across these 16 countries, weighted by the number of daily observations of infections. So obviously here, China basically gets much more weight than other countries that have less infections early on. So just to kind of highlight what we get, the reproduction number, if you do it with this very simple, what we call robust statistical method, is about 3. Okay, but the thing we'll highlight is that it's a very wide confidence interval. The 95th is 6.5 reproduction number, and the 5% is 1.1. Okay, and of course, these estimates actually are not so far away from the leading epidemiological models. Our confidence intervals are a bit wider, but certainly, the 3 fits pretty comfortably within what other people are finding. We make a bunch of conditional forecasts for a log of IT. So these are some forecasts so we're going to lock down the parameters in January and February, and we'll make forecasts for March and April. Okay, the red dotted lines represent the 95th confidence intervals, and then the black line is our conditional forecast, and the blue line is the actual data. So for instance, if you look at China, right, our model predicts, right, this black line, but of course, China intervened massively, so the model basically is going to be off from the point of view of China. But for most of the other countries, you see some curve flattening, but they're all within basically the standard error band that our model will predict, right, other than basically China and South Korea at this point. If you turn to the Western countries, you see a very similar picture. The model fits pretty well. Actually, for the US, the model basically does not fit as well. Some of this we think has to do with the underreporting of cases. So in the paper, we deal with a bunch of issues about how to deal with underreporting, and I won't get into that just given the brevity of time. But basically, our sense is that the parameter of the reproduction number of 3 and the Y standard error band captures some basic extrapolable parameters from the point of view of COVID-19 for lots of different locations. So let's drill down a bit to kind of think about what the implications of the stochasticity means. So this is a very detailed forecast for the USA on March 31st.
Just giving you 1 minute.
Perfect, absent intervention, right? So what the model would basically say is that, look, in 3 months, right, the deterministic model would say there's 10% infection. Our model would say about 3%. But the big thing is there's a 9% standard deviation, right? So in the short run, basically, variance is the entire game as far as driving actual outcomes of interventions. The other thing we'll mention is there's a lot of talk about reproduction number of 1, but if you look at even kind of slightly reproduction numbers away from 3, such as 1.75, you basically have much more manageable infection numbers. For instance, even at 12 months, at a reproduction rate of 1.75, you get about 1% infection. But also, again, with a very wide standard error band of 6%. We then basically link this to economic data, right? We can basically calculate then this economic data using the valuation model. And we do some calculations based on some parameters. I don't have time to get into all the parameters, but essentially it's a very straightforward exercise that's done often in financial modeling. So then we can kind of generate essentially the valuation damage. For the same set of epidemic data, we can generate the damage to economic valuation. First conclusion is it's pretty easy to damage wealth when you have an epidemic, right? So for instance, if you basically have a high reproduction number, a lot of industries would eventually basically be kind of destroyed for very plausible innocuous assumptions about cash flow growth, okay? So what, the other thing you can do with the model is to introduce vaccines. Vaccines obviously help stabilize the distribution, but the conclusion we have is that vaccines actually are not that useful from the perspective of managing the epidemic, because, you know, for all the expectations of how long they're going to arrive, it'll take way too long. For instance, a vaccine that's expected to arrive in 2 years is still going to give you, absent change in behavior at 9 months, 43% infection with a standard error of standard deviation of 32%. But actually, vaccines are very good for wealth in the terms of like pricing. Right. The market understands that a lot of the valuation, a lot of the damage could be coming a long time down the road. And in that sense, having a vaccine is very good for stabilizing markets. And we think that both of this is very consistent with sort of the evidence that we're seeing right now. So conclusion, luck plays a huge role. Deterministic models overshoot. Conditional variances are really key for characterizing COVID risk. R0 is not a sufficient statistic when it comes to managing epidemic risk management in kind of an economic sense, and the role of vaccines also plays a crucial role when it comes to managing the economic crisis. Thanks a lot.
Wonderful. Thank you very much. Looking for any questions. Margaret, I see your hand is raised, but it's probably from the previous one. But
nope, I have a question.
Okay, great. So
right.
Please ask.
Thank you so much for your talk. Can you please explain a bit more what you mean by homogeneous mixing?
Right. So I think the standard assumption is that if you have a population, the equation that governs dynamics of infection assumes that there's kind of equal chance that people in a population can run into each other essentially and transfer the virus. Now, of course, that's not true in reality. That's why most epidemic models tend to basically use, try to capture a lot of the non-homogeneous mixing to account for that in terms of these predictions. And of course, there's some usefulness of that, but then the models become extremely difficult to solve, and that therefore makes the implementation of these epidemic models into an economic context less useful. And that's sort of what we would need to manage the economic crisis that's COVID-19.